Log on, tune in, find out. Another good idea from Cambridge.
Kinetic model of chemotaxis. And as you saw with Vincent Calvez, they swap and we will move forward on the same kind of topic but afterwards.
Okay, thank you very much, and I would like to thank the organizers for the invitation. It's a pleasure to be here. Apologies for changing the order of the talk. We thought it was better to do the theoretical part of these things first and the applications afterwards. Okay, so this is a joint work with Vincent Calvez, Susana Gutierrez from Birmingham, and Benoit Pretin. And it's about chemotaxis. So we all know what chemotaxis is, so let's go quickly over this. It's the motion of cells in response to a chemical substance. The game you play is that the tendency of cells to aggregate is balanced by their tendency to diffuse, especially if you write down Kelder-Zegel. Perhaps it's a macroscopic statement. So I have diffusion and aggregation. And if you look at individual cells, you see runs and tempos. Like they move in a straight line, and they stop and change direction, move in a straight line, stop and change direction, and so on. So this is the kinetic model I want to talk about. It's called the Othmer. It was introduced by Othmer, Dunbar, and Alt many years ago. On the left-hand side, we have F is the density of the cells, and S is the chemoattractant. So on the left-hand side, we have the kinetic part. So that's, if you like, that describes the runs. And on the right-hand side, we have T is the turning kernel, and it's a positive functional of the chemical. I'll give examples in a minute. So on the left, we have runs. If you like, the right-hand side describes the temple, and here you have a competition instead of diffusion aggregation. You have a competition of run or stop and change direction. Okay, so that's the equation for F. So let's see, the T of v prime is a measure of the probability of changing from velocity v prime to v. So think of it this way: v prime, v, so T, v prime. Okay, for S, in real life, you should probably write down a parabolic equation for S, but if you are a mathematician, you simplify it and you write down an elliptic equation. For example, minus Laplacian S equals rho. Let's see if I can point to this. Minus Laplacian S equals rho, or a slightly better elliptic equation sometimes, S minus Laplacian S equals rho, or the three dots are parabolic equations. Okay, so for this model, I want to ask whether solutions exist globally or whether they blow up in finite time, and so on and so forth. And the tools I'm going to use come under these names: Strichard's estimates and dispersion estimates. They come from the theory of dispersive equations. Okay, but before we go there, because they look a little strange for this sort of equations, especially if you haven't seen them before, so I'm going to show you a simpler example of Strichard's estimates and how they are used. So I'll take my favorite example, is the wave equation. So UTT minus Laplacian U equals F. You give it some initial data. Let's do everything in 3 dimensions, because that's the only dimension in which I remember the numerology. So you give it some initial data. And let's do the simplest possible case. Let's take in the energy class. So what people used to do before Strichard's is they used to use Sobolev and energy. So Sobolev tells you, for example, if you're in 3 dimensions in this class for the wave equation, it tells you this. So UT in L6. You can bound that by U in H1, that's Sobolev, and then energy tells you that this is less than F in H1 plus G in L2 plus the integral of 0 to T F S L to ds. That's the kind of thing people used to do before Strickhardt. You think of your space-time, so that's x, that's t, you think of it as foliated by planes at constant t, and on each of these slices you say something about some norm of u. In this case it's that norm, it's bounded by those norms. The philosophy behind Strickhart's estimates, maybe can I write here? The philosophy behind Strickhart's estimates is that instead of doing that, instead of thinking of estimates along time slices, you use norms in space-time. And if you do that, you gain something. In this particular case, with this numerology, you can do u in a late of t and x is less than various constants that I don't want to worry about, less than the same thing. Less than this. So with your data, f and g on the right-hand side in the energy class, you go up from 6 to 8. That's a lot of gain. These are linear estimates, and if you want a linear estimate to be useful in a nonlinear problem, it has to be of this sort. It has to say that you gain something that you didn't expect to gain. So what can you do with this? Well, you can do various things. For example, if you have a nonlinear equation, utt minus Laplacian u equals f of u, with this nonlinearity, okay, to get to 8, say something that behaves like a fourth power, then you say u in a late is less than this thing. So it's this quantity that, let's call it d naught for data at 0 plus your right-hand side. Okay, I don't want to be very precise, but on the other hand, okay, you have to do this on a time slab, space-time, but you do it from 0 to t. Plus 0 to t u to the fourth in L2, that's with respect to x dt, so this is 8 and 4. You can bound this by t to the 1/2, like Cauchy-Schwarz, you get u L8 in space-time, same norm, 2 squared, right? So now, what can you do with this? Either you assume that this is small, so you have a late, right, raised to a power multiplied by this power of t. So either you assume that t to the 1/2 is small, and you get local existence, or you assume that this is small, and if you play your cards right, you have to do it in a different way. But I'm cheating a little bit. Either you assume that this is small now, and you prove global existence for small data, or if you're really lucky and your nonlinearity is such that the corresponding energy for the nonlinear equation is positive, then you have local existence in the energy class, say by running an argument like this, and positive conserved energy, and you get global existence. So if positive energy, global existence for large data. If positive energy, global existence for large data. So that's the sort of thing you do with Strickhardt estimates. Either you get some sort of local existence in your favorite class, or you assume small data and then you get global existence, or if you're really lucky and you have positive energy, then you can combine this local existence with the fact that the energy is positive and conserved and get global existence for large data. That's the sort of thing Strickhardt estimates do for you, and it's due to this gain that you go from 6 to 8. Okay, now let's look at this Strickhardt estimate. So these are due to Castella and Pertam and Mark Hill and Terry Tao. And I don't want to go into too much detail. There's always a lot of numerology with these things. So you have the kinetic transport equation with the right-hand side g, and you have some initial data F naught, And now you estimate a norm which is much more complicated than this. It's a mixed norm in time, space, and velocity. And you estimate it by, you estimate this complicated norm by some norm of the data and some norm of the right-hand side. And if this is to be useful, and if you believe all these philosophical things that I said before, there has to be a gain somewhere. So where is the gain? The gain is here. So Q is less than P. So in the left-hand side, we have P and Q, P in x and Q in velocity. In the right-hand side, we have exactly the opposite. Right? So here we have P in x, Q in velocity. Here we have Q in x, P in velocity. So this takes, and P is the large exponent, Q is the small exponent. This takes the large exponent from x and puts it on V. So that's where you gain. Now, of course, you pay a price. Right? On the left-hand side, you have the small exponent on V, and in the right-hand side, you have a large exponent on V. Well, it turns out for our purposes, it doesn't matter. The velocity space will be bounded. This is about cells. The velocity space will be bounded. And this will combine very well with the structure of the equation. And it turns out all the action is in x, not in V. So that's where the gain is. You take the large exponent from x. On the left-hand side, you have a large exponent on x. On the right-hand side, you have a small exponent on x. That's where the gain is. And there is always a lot of numerology with these things. Okay, so let's see dispersion estimates. Again, these go back to early version to Bardos and de Gonde, and then completed by Castella and Pertam later. Okay, again, you have the kinetic transport equation with 0 in the right-hand side and some data F naught. And it turns out you can estimate mixed LP, LQ norms on time slices now. These are sometimes called pre-Stricherts. Once you have an estimate like this, there is a standard harmonic analysis machinery that you can feed this into to get Strichert's estimates. And then on the right-hand side, you have again, you flip P and Q as before, and you have in the denominator, you have a power of T, which you can think of in various ways. It's either, if you think of large T, it's the decay rate. The solution in this particular norm decays like this. Or if you like, you can think of it as the price you have to pay. That's how it enters our proof. It's the price you have to pay for this little gain of changing P and Q. And the solution of this problem is very easy. It's just F naught x minus tv comma v, and the estimate simply says that if you have a function of x minus tv comma v, you can estimate it like this. Okay, so let's go quickly over Keller-Zegel. What kind of results are we after? So where do you look for guidance as to what kind of results can you expect for the microscopic model? Well, you look at the macroscopic, at the corresponding macroscopic model. So let's recall very quickly what Keller-Zegel is and what results we have for Keller-Zegel. So again, the equation for n, I wrote it down earlier. For the chemoattractant, if you are a mathematician, it's minus Laplacian. Oops, sorry. It's minus Laplacian s equals n, or another elliptic equation, or parabolic. In one dimension, you never have blow up. You always have global existence. Diffusion wins. In 2 dimensions, things start to get interesting. You have global existence if the mass is small. You have blow up if the mass is large. And the proof of blow up is extremely simple. You take the second moment of the solution, the integral of x squared and tx. Usually you differentiate this thing twice. If you look at other equations where this quantity is used to prove blow up. But here, if you differentiate it once, you get lucky and you get a constant, which you can make negative if the mass is large. And this very simple one-line argument gives the sharp constant for the mass. Okay, you have blow up if the mass is bigger than 8 pi over chi. You have global existence if it's less than that. Right? Okay, so the derivative of that quantity is negative, so is equal to that negative number. So if you integrate it, it becomes, the quantity itself becomes negative in finite time. global existence, let's keep this transparency. It says that you can prove it. There is a way to prove it, to prove global existence for small mass, but doesn't give you the small mass. So let's save a little bit of time and go straight to the argument that does give you the best possible constant. This is due to Blanchet, Dolbeau, and Pertam. You take the energy or entropy or whatever you want to call it. This you can calculate precisely its derivative, and it turns out to be given by this quantity, so it's negative. So you can write down an estimate. This is less than itself at time 0. And then you combine it with log Sobolev, log Hardy-Littlewood Sobolev, sorry, for which the best constants are known from, for example, from an old paper of Beckner's. And if you combine these two, right, there's an m over 2 here, there's a chi over 4 pi there, they combine and they give you the 8 pi over chi. Okay, so if you combine them, you get control of this quantity, integral n log n. What does that mean? It means when you start, you have conservation of mass, so you are integral of n, you are in L1, and now you have gained a little bit. You've gone from integral of n to integral of n log n. You gain a little bit. Turns out that's enough. With a lot more work, you can prove global existence. And if it's exactly, the mass is exactly critical, you have, you can say blow up, but in infinite time. Solution exists globally, but it gets large as time grows. So this is a very interesting problem in 2 dimensions. Higher dimensions, okay, you would think that the analog of the 2-dimensional result is take the LD over 2 norm, and if it's small, you have global existence. If it's large, you have blow up, but life is not so easy. For the blow up, there is this perhaps a bit complicated inequality. If you have it, you have blow up. If you want to see so this goes back to papers of Corias, Pertam, and Zag, and Corias and Pertam, 2004 and 2006. And if you want to see the latest results, you can look at this preprint of Calves, Corias, and Ebde. Okay. Now let's go back to the kinetic model, and the results we are after are of this sort. Global existence under certain conditions, perhaps smallness conditions. Blow up if things are large. And the paper that started this series of results is due to Shalub, Markovich, Pertam, and Schmeisser back in 2004. So they proved that if, in 3 dimensions, if the turning kernel is this, or if it's bounded by that, S of x plus epsilon v, x minus epsilon v prime. So if you like, v prime is v, is x, x plus epsilon v is a little bit ahead, x minus epsilon v prime is a little bit behind. It's as if a cell sitting at x is looking a little bit ahead and a little bit behind, and that tells it what to do. Under these conditions, you have global existence of weak solutions. They also prove in the same paper that if you do diffusion limit for this kinetic model with this turning kernel, you get Keller-Zegel in the end. Now, with the same method, Huang, Kang, and Stevens proved a little later that if you go to 2 dimensions, you can include gradients. Right? So maybe this is about gradients. Right? There are no gradients in this assumption, and maybe it's much more natural to have gradients in your hypothesis for T. So in 2 dimensions, you can do it. The proof of this is exactly the same as the proof of that. You have x plus epsilon v, gradient at x plus epsilon v, s at x minus epsilon v prime, and also the gradient at x minus epsilon v prime. By the way, the proof of this, it doesn't use the dispersion as I have described it here, but you have this structure, delocalization, if you like. You're not at x, you are either a little bit ahead or a little bit behind. And so that's one thing, one piece of the structure, this x plus epsilon v, x minus epsilon v prime. And you have the structure that you get if you just solve the kinetic transport equation. You have that f naught of, what was it, x minus tv. And these two combine, they give you very nice convolution structures which if you use them cleverly, you can prove that global existence here. Okay, so this is where we started, and this is what we could show. If you are in 3 dimensions, you can run an argument of the sort I described before with a 3 Hertz estimate. Okay, so if you have small data, in the L3/2 norm, in this case, that's a critical norm, it's d/2, then you can prove global existence, right? I have removed epsilon, that's epsilon equals 1. And you can have both gradients in 3 dimensions if you are willing to assume a smallness condition. Can you remove the smallness condition? Can you remove that? I don't know. You can remove it if you remove one of the gradients. So that's what the mathematics tells you. So if you bound your t by x plus epsilon v, x minus v prime, gradient at x plus v, or you can omit that gradient and include the other, that's the same, then you have global existence without a smallness condition. Okay, I still don't know, it's still an open problem whether you can have both gradients. Am I saying this right? Yes, it's still an open problem whether you can have delocalization, both gradients, and no smallness condition. Okay, let me sketch the proof of the second theorem. So I can show you very quickly how the structure works together with the dispersion estimate as I have described it. Okay, you can write down what the solution is. Duhamel's principle. You have many terms in the right-hand side because your turning kernel is a sum of many things. And this is one of them. This is what you get from one of these terms in the right-hand side. That's not the easiest one to estimate. It's the easiest one to explain in a talk like this. So so you get your x minus SV for technical reasons that I don't want to go into. We have turned it into s minus 1. The same here, x minus SV minus v, s minus 1. And now you choose P and Q appropriately, and you take a mixed norm, LPX, LQV. You pass it inside the integral, so here it is. That's exactly the same as in the previous transparency, this quantity in here. You have LPX, LQV. And now you apply the dispersion estimate of Castellan per term. You pay this price. Alpha is that exponent we had before, the dimension times 1 over P minus 1 over Q. And you flip the exponents. Right? You have Q in x, P in velocity. So the small exponent is in x now, and now the structure comes to your aid. You have to take this norm first, right, the LPV norm first, but V comes up only here. There's no V there. So V comes up only here. So this LP norm hits rho, get that, and the LQ norm hits the gradient. Okay, so far so good. We are after a Gronwall inequality, but this is quadratic, of course, quadratic nonlinearity. So we have one thing there and one thing there, and if you want to conclude from this, one of the two has to be estimated a priori. The only conserved quantity you have is the mass. One of these two has to be estimated a priori by the mass. And indeed, if you can do a very simple elliptic estimate, if Q is small, then you can estimate the gradient in LQ. Q is less than 3/2, you work it out. You can estimate this in LQ by the mass. And rho in LP, you can boost it up to that. Velocity space is bounded, so that you have in the right-hand side this quantity, in the left-hand side the same quantity, and you do a Gronwall inequality. The difficulty with adding the second gradient here is that, well, each of the gradients on its own you can estimate. You can do something similar to this. But each time you do that, I'm omitting all the numerology here. Each time you do that, you get restrictions on P and Q. And you cannot find, at least we could not find when we tried this, one set of P and Q that could do both terms. You can find a set of P and Q that can handle one of the gradients, and you can find another set that can handle the other, but not one that can do both. Okay, so we are after eventually something similar to what we have at the macroscopic level, right? Blow up if something is large, if the mass is large. How are you going to find such an example? Well, one way to think about it is you take whatever method you have that proves existence and you stretch it to the limit. And maybe if you stretch it to the limit where the method fails, maybe that's where you find the blow up. So with the dispersion method, you can prove with dispersion and Strichhardt, you can prove theorems like this. Start in 3 dimensions. If you are in 3 dimensions and you estimate your turning kernel by the L infinity norm of S to the first power, you cannot do it. That's where the method just about fails. 1 minus epsilon, no problem at all. The method works fine and you get global existence of weak solutions. Or you can play the Strichhardt's game and take the power here to be 1 and take the L infinity norm and make a smallness assumption. Or you can reduce L infinity down to LP, in which case you can take even a power larger than 1. You can go up to this. So the dispersion method in 3 dimensions, and if there is a little time left, I'll show you why the exponent is 1. It's very easy to see why it is 1. So in 3 dimensions, the dispersion method, if you stretch it, that's where it that's the best it can do. S in L infinity to the 1 minus epsilon. And in 2 dimensions, you have the analogs of these results. In 2 dimensions, okay, let's look at this first. So it's gradient now in L infinity to the 1 minus epsilon. S itself is not a problem at all in 2 dimensions. S itself, you can take it in L infinity, you can raise it to powers, you can do anything you like. S itself is so not a problem in 2 dimensions that you can take the L infinity norm and raise it to a power and take an exponential of that. And again, you hit a critical exponent. So you can do it with alpha strictly less than 1. If it's 1, you can prove global existence of weak solutions. If the mass is small, that's a constant the proof gives, m less than pi. Okay, so right. Okay, let's see. We have a bit of time. Let's see very quickly why the critical exponent is 1 in 3 dimensions. So you just do it as before. You write down what your solution is. It's a sum of various things. You have that comes from the turning kernel, L infinity to the alpha. You have rho. That's what the structure gives you, x minus SV. And you do as before. You take LPX, LQV. You apply the dispersion estimate of Castellan per term. You pay this price, s to the 3, 1 over q minus 1 over p. And okay, it's done a bit fast here, but if you work it out, you can estimate by rho in LQ and s in L infinity to the power alpha. And then you can do very simple elliptic estimates for s. You can estimate this by the mass, something that has to do with the mass, constant times the mass perhaps, to the p prime over 3, constant times the mass to some power. It doesn't matter. To that power, p prime over 3. And you can estimate the LQ norm. You can put it between the L1 norm and the LP norm. So very simple interpolation inequality. Pick up this exponent. And now you put them together, and you have the following difficulty. You have, it's Gronwall you're after. It's Gronwall you're after. So you have LPX LQV in the left-hand side. That's LP of rho, but we can boost it up easily to that, so no worries. It's raised to this power, alpha p prime over 3 plus p prime over q prime. That's what the previous transparency gave us. And here's the price that you pay for gaining that, for flipping p and q. And now you need 2 things. You need this exponent to be less than 1 for this integral to converge at 0. And you need this power not to be bigger than 1, because otherwise you cannot do Gronwall. And you cannot have both. That's where it fails. But if alpha is 1 and you try to do this exponent, try to make this exponent smaller than 1, you make the other one bigger than 1. It doesn't work. If alpha is strictly less than 1, there is a little bit of wiggle room And you can do it. You can find P and Q such that this is less than 1 for convergence, and the other exponent is exactly 1 for Grunwald. So if you stretch the method to the limit, that's what you get. Is this best possible? Right, let's go back. Okay, so is this best possible in 3 dimensions? I don't know. But this is the exact analog of this in 2 dimensions. It's the gradient to the 1 minus epsilon. And this is best possible. I know that this is best possible because we have found an example of a turning kernel which is of the order of the gradient, for which you have blow up in finite time if the mass is sufficiently large. So what does this kernel do? I don't know, perhaps it's a mathematician's kernel. So if a cell is sitting at X, trying to decide where to go, the gradient points this way, so V prime is this. So these are good directions, and these are bad directions. So this turning kernel says the cells would always choose, plus is the positive part, right? I should have said this plus is the positive part. So you take V dot gradient as positive part. So the cells always choose, it's like saying that the cells always choose good directions. And what we can show for this turning kernel is the following. If you assume spherical symmetry and the mass is small, then you have global existence. And if the mass is large, then you have blow up. The 2 masses here are very far apart. So what I mean by this is that there is a mass, there is an M, let's call it M1, such that if your mass is below this, you have global existence. And there is another M, which is much, much larger than that one. If you are there, you have blow up. Okay, obviously, that's not the result you expect. It's still an open problem to close this gap, to find one single M with a property below that you have global existence, above you have blow up. We cannot play the same games that you play with Keller-Zegel, where you use the energy to find the critical mass, to prove global existence for small mass, because there is no energy for the kinetic model. The only thing that you have is conservation of mass, and then you are on your own. Okay, so here's a quick sketch of the blow-up proof. You do the same thing as for Keller-Zegel. You take the second moment of the solution. Right, and remember, for Keller-Zegel, you differentiate it once and you get lucky and you get a negative constant if the mass is large. Here you don't get lucky. What you get is this quantity. So you go on and you differentiate again. Perhaps this is not a surprise because you have to differentiate again because you have x squared and you have to bring this down to a constant, and the kinetic transport equation has a first derivative in x. So you have to hit the x squared twice with a derivative with respect to x to bring it down to a constant. The Keller-Zegel equation has a Laplacian in the right hand side. That's already 2 derivatives. Okay. So you differentiate it twice and you get a sum of 3 things. You get a term that behaves like this. V squared is exactly equal. That's exactly equal to V squared f txv. You get a term that looks like this. You have x dot v, v dot gradient positive part times rho, and you have a third term which is x dot v modulus of the gradient of s times f. And what can you do with these 3 terms? The first one is completely trivial because the velocities are bounded, so you just get rid of this and the rest is the mass. The integral of f is the mass, so that's less than the mass. The second one, if you do the v integration, if you do this integration, dv, right, you see you have x dot v, so v dot something else. That gives you a constant times a dot product between these 2 vectors, times rho. And if you look at the proof of blow up for the Keller-Zegel model, this is exactly what you get at this step. You get exactly this integral, x dot gradient s times rho. This turning kernel is designed to do this step. From the mathematics point of view, this is what the turning kernel is designed to to make this line work. This plus? Oh, okay. If you think of the v integration, the velocity space is the ball. X dot v. So you're just integrating on half the ball. That's what the plus. Right. So this is exactly what you have for Keller-Zegel. It turns out it's exactly equal to minus cm squared. You write down what the gradient is, you do a symmetrization trick, and you get exactly minus cm squared. So far, so good. Spherical symmetry has not been used. But now you have the last term, which you can estimate by m squared. It's of the order of m squared, but unfortunately with a constant that is too large to be absorbed into this. So you have to do something else, and this is where spherical symmetry comes in. It's spherical symmetry. You can write everything down explicitly, and you're in 2 dimensions. You write everything down and you calculate. And it turns out this is the derivative of a positive quantity. This came with a minus sign, right? If we go back to the previous transparency, it had a minus sign. So it turns out it's the derivative of a positive quantity. So if you integrate once, if you go back once, you have c from various other things. You have mass and m squared. You have c from the initial data. You have cm minus cm squared from these 2 terms. And you have p of 0 minus p of t. So this troublesome quantity, which is of the order of m squared, you can just get rid of it at this point. And you're left with that. And again, you say that if the mass is large, then things become negative in finite time. Spherical symmetry is used only in this last step to write down exactly what the modulus of the gradient is in the spherical symmetry case. Okay, then just the last transparency, one before the last. How about global existence? So now we want small mass implies global existence. Why not try Strichard's, right? If you believe that philosophy. Unfortunately, you can try Strichard's, but you hit an open problem. You hit an endpoint case of the Strichard's estimate that is, it was left open both by Castella and Pertam and later by Kiel and Tau. It's deceptively simple. The exponents are 2 and 1, and it's the solution of this equation. You can write it down in a very simple form, and yet this is still an open problem. So we had to do something else to prove global existence for small mass. We find a comparison function, and if we assume that the initial data are below this comparison function, then we prove that the solution remains below that comparison function. Explain this later. I can explain this some other time in more detail. There's no time. This is the last transparency. Open problems. Well, you can write down many open problems in this field, but I think perhaps these are some of the most interesting. Obviously, find the critical mass here. Remove the assumption of spherical symmetry. It's not there in Keller-Zegel, so there must be some way to remove it for the kinetic model. If you want to be a little more ambitious, is it possible to characterize the turning kernels for which blow-up occurs instead of just having specific examples? And can you say anything in, I say higher dimensions, but 3 dimensions perhaps? Okay, thank you very much for your attention.
We have time for a very short question.
Space dimension 2, you had the specific turning kernel. When you do the diffusive approximation, does this result in the classical turning kernel you have chosen?
Sorry, the one with x plus epsilon v, or no, for the blow up? For the blow up, yes, it does.
Really reflects the
Yes, it does. And actually, when you look at these 2 masses, I said before that there has to be one in the middle, where you have on the left you have global existence, on the right you have blow up. If you do that, you find the corresponding Keller-Zegel. The blow up mass for that is exactly what you get for this. So maybe we have the best mass. I don't know. Maybe the blow up proof is sharp, perhaps, I don't know, and gives you the best mass. But the existence proof is too crude to handle this.
Okay, thank you very much.
Thank you.